Okay. Good morning, everyone, and welcome 140 session of DDP and Applied Mathematics Seminar. It's an honor for me to introduce Professor Jose Pedro Rodriguez Ayllon, postdoctoral from Fluminense Federal University. Professor Rodriguez completed his doctoral study in the University of Houston in United States of America. In this occasion, Professor Rodriguez will give the lecture entitled on Pareto equilibria for generalized heat equation with no local nonlinearity. Welcome, Professor Jose Rodriguez, and you can start.
Okay, thank you very much, Professor Mako. We are going to start with our presentation, and we are going in this work. It is a joint work with Professor Limako and Professor Bautista. That it is another postdoc here at the university. What it is our work about? We are going to study Pareto equilibrium on the objective control problems. What it is our question? First, we are going to check that there is indeed an agent that it is going to exert some sort of control over a differential equation such that we want to drive the state a variable to a certain place, to a certain given state that we are wishing to achieve. In this case, we want this variable to be as close as possible to two targets or objectives. And the work says that it is a non-local non-linearity. It is with respect with this term, the a in parentheses, there is an integral that it is an average over the gradient of the function u. And we are taking an average of the gradient, and that is our non-local non-linearity in this work. Okay, what is our objective? We want to drive through a control uv, through this control v, we want to drive the state a variable u as close as possible to two targets, in this case uit, which are L2 corresponding to the optimization criteria. That is, we want to minimize each functional such that the final state of the system it is as close as possible to ui, and we have the regularization term of the control. And we are seeking those solutions within a control, within a collection U, that it is the admissible control set. And the OIs are the regions where we wish to drive our agent U. So what it is happening? This O sub I may represent a place where we are taking measurements. So we want in that place that we are taking some measurements, and we want our final state as close as possible to our objective U sub I in the case of the functional J sub I. Okay, so that is our objective. And our control, it is going to act within a fixed set omega, that it is at the region where it is going to exert the control. It is going to exert some actions, so we are going to drive the system to our state that we wish to go. So this, and again, as in our reference and as it is in the literature, we assume that U, it is a closed convex subset of the space L2 omega A0T in our case. Okay, so what is the definition of a Pareto equilibrium? As we said, we want to drive the state U as close as possible to each objective U sub I, but these objectives may be perhaps conflicting, or may, if I achieve one objective, I may go far away from the other. One example of this, it is when you are buying something, for example, a car, you want the best quality at the lowest cost, but normally if you have equality, you have to pay more. So you need to achieve a compromise. In this case, that is what the Pareto equilibrium says to us. What do we have here? We have a control V hat. It is a Pareto equilibrium within the admissible control set. Within the admissible control set, we have that a control, it is a Pareto equilibrium. If there is no other control in the admissible control set, such that we have that the value of the functional V at B, it is less or equal than the Pareto equilibrium, and we have at least one inequality, and that is I cannot improve each of the controls without affecting the other control. That is the definition of a Pareto equilibrium for us, okay? So we want, in that context, to exert a control on the system such that we are going to drive our system, our state variable, as close as possible to the given variable j sub I, as close as possible to the target. So we want to minimize that Euclidean distance, and we are using the regularization term of the control. So we have two objectives, functional J1 and J2, okay? So we have those two objectives. We also have a useful criteria that it is called Pareto quasi-equilibrium. That what is a Pareto quasi-equilibrium? A control, it is called a Pareto quasi-equilibrium if there exists a constant alpha and the Gatot derivative of the convex combination of J1 and J2 in the direction of W minus V hat, and that is, if we are going to get away from the Pareto quasi-equilibrium, our convex combination, it is going to increase, okay? So it is saying that the derivative, the action of the derivative towards that deviation, it is going to be greater or equal than 0. And that is, it is not going to decrease, it is going to increase. That is a Pareto quasi-equilibrium. This is a technical notion that helps us in the proofs in our work. And obviously, if we have a Pareto equilibrium, it is going to be a Pareto quasi-equilibrium. The convex holds if the functionals J1 and J2 are converse, okay? The converse, it is going to hold if the functionals are convex. Okay, so as we said, we want to show how a control V can influence systems like 0, 1, and 0, 2, so that the final state is as close as possible to UIT for I1 and 2. That in the Pareto sense of optimality. In this case, our system, it is going to live in a cylindrical domain where omega, it is a subset of Rn with a smooth boundary within a finite frame of time that it is t greater than 0. We also assume that we are going to take the measurements in open sets that are subsets of omega, and those open sets might not be non-empty, okay? So that might represent that there may be a conflict within them, as the example of the price and the quality, which if you want more quality, you have to pay more, but you want to pay as little as possible. Okay, our first case of a study, it is the system where we do not have the bilinear control. We're going to study that later. So we have this system, and where our control, it is V in the L2 omega S0t. And we have our function A, which we assume A to have this behavior. A, it is going to be a C1 function such that A, it is going to be greater to a positive constant and less or equal to another positive constant. For some positive constants, A0 and M. And F, it is going to be a twice differentiable continuous function, zeta function, such that we are going to have that F of 0 is S0, and F, it is going to be it is going to be within a cone, within the cone M absolute value of X. It is going to live within that cone for some positive constant M1. That is our hypothesis for the functions A and F in this work. Okay, based on those hypotheses, if our system satisfies those hypotheses and we have our initial state of our system that it is within H01 omega and our control it is in L2 omega 0t, then we have the result that there exists a unique regular global weak solution of our system that satisfies the following energy estimates. Okay, and we have those energy estimates that it is bounded in the L2 infinity 0t L2 and H01 norm. It is bounded in the L2 0t H2 norm, and the derivative with respect of time, it is bounded in the L2 0t H minus 1 omega, and those bounds are going to depend on A0 M M1 T, the initial value, the norm of the initial state, and the norm of the control. Okay, so we're going to see what happens with our Pareto optimality notion. We proceed with a concept called scalarization in the references. So what do we have here? We are trying to optimize two functionals. So that is a multi-objective optimization problem. So one famous technique, it is the one called scalarization. And in this case, it is weighted sum. So what we are going to do for alpha within 0, 1, we're going to write a new functional that it is a convex combination of J1 and J2. That is a weighted sum in which the weights are equal, in which the sum of the weights are equal to 1 and the weights are non-negative. And we are going to check the optimality conditions. So we proceed to compute the Gatot derivative of the functional J alpha and in the direction of W minus B. And that derivative gives the following expression, and that is, and we are going to have the derivative of the functional J sub alpha. It is going to be of the convex combination the following, okay, ut minus u1t with a variable zt, and we are going to see the variation of W minus V, which these two first terms may be interchangeable by a term phi multiplied by W minus V. We're going to see what it is that. So Z, it is the solution of the following system, which is a linearization when we are computing the limit when we introduce a perturbation of the original system with that epsilon and with that control, which it is reflected here, and that is the perturbation of our system. And phi, it is the solution of the adjoint of the system Z. It is the adjoint of that system C, okay? So we also have the following proposition. These results are going us to help prove that the functionals are convex. So it says that under the hypothesis that we have of the functions A and F, and if W and V are in L2 omega S0t and the controls and the states satisfied that are in H01, we're going to have that the systems that the system of the derivative and the adjoint are well posed, have a unique solution, and satisfy the following energy estimates. Okay, those energy estimates are dependent on the constants that we already know, those constants of the systems. And then with that, we are going to recall two propositions for proving our Pareto equilibrium in our setting. From the previous work, because this work, it is an extension that of a previous work made by the Professor Limaco and his collaborators, it says that if we have a Pareto equilibrium for the criteria J1 and J2, then it is a Pareto quasi-equilibrium. And then again, for the convex, if alpha belongs to 0, 1, and V hat minimizes the convex combination, then V it is a Pareto quasi-equilibrium. And if alpha it is between 0 and 1, it is a Pareto equilibrium. We are going to see what happens when we have alpha in this first case. So what do we have here? We are going to focus where mu it is going to be greater or equal, or it is going to be positive. Otherwise, we are not going to have the convexity. So what says, if we assume that mu is positive for each alpha between 0 and 1, there exists a control V hat such that V hat it is greater, it is less or equal than any other value in the control set. Okay, and in particular, that is a Pareto quasi-equilibrium. To prove that, what a result do we need? We need that the functional in 0,3, it is weakly lower semi-continuous and coercive. And that is and this is some scheme of our proof. So in order to prove that it is weakly lower semi-continuous and coercive, it is just necessary to prove for each j sub I. So we are going to use the energy estimates of theorem 3. Indeed, so when we take a sequence Vn in U that weakly converge to U, and we are going to denote Un and U, the respective solutions corresponding to the system 04 that corresponds to Vn and V, then what do we have? Since Vn converged weakly to V in L2 omega 0t, and we have that the norm of V, it is going to be less or equal than the lim inf of the norm of Vn L2 0t, okay? And therefore, we are going to have that the supreme of those Vn, it is going to be bounded. Therefore, from the energy estimates, we have that the U sub n's are bounded in L infinite 0t L omega intersection with H01 with L2 0t H2, and the derivative of that sequence is also bounded and satisfies, and it is bounded by constants. Okay, here, since we have that V sub n's are bounded, why are bounded? Because we have weakly convergence, okay? So if those are bounded, we can extract subsequences that we are going to denote U sub k such that those subsequences are going to converge weakly in L2 0t H01, weakly start in L infinite 0t L2, and in UK and in L2 0t H-1 omega. And by the Aubin-Lyons assignments, we can also extract another subsequence denoted again UK such, and that subsequence it is going to be convergent in L2 0t and in C and in the continuous function 0t L2. So here this part it is important of the continuity by the Aubin-Lyons Simons theorem, and we have here okay that it is bounded in L infinite. This L infinite for L2, it is going to ensure that we have the second case of the lemma. So we have the convergence in the continuous 0t to L2 omega strongly. Therefore, we have that it is that the limit a function and that the functions are defined in time at time t. So we can take a test a function phi in H01 omega and eta in C1 0t such that eta, the eta of t it is 1 and eta of 0 is a 0, and we can estimate taking the actions that by integration by parts that this this left hand side of the expression of the action of UKT over the function phi ns, it is going to be by integration by parts as the action of UKT over phi minus the action in H01 omega of UK and 0. Okay, so if we take the limits since we have those convergence established, we are going to have that UK at T of acting on phi, it is going to converge to UT at phi acting on H01 omega. That is, if we have the weak convergence in H01 omega. But since H01 is dense in L2, then we can also take phi to be in L2 omega. Therefore, we have weak convergence in L2. Hence, we have that UT L2, it is less or equal than lim inf 2 of the UN LT. So combining this with the first, combining this with the other air result, what do we have? We have that the JIV, the value at the limit V, it is going to be less or equal than the lim inf of JV sub 1. Therefore, the function, it is weakly lower semi-continuous, and the coercivity comes from the fact that JIV, it is greater or equal to mu VL infinity. So if we have a coercive function that is weakly lower semi-continuous, the literature of optimization and calculus of variations says that we are going to have a minimum, and therefore we have our Pareto quasi-equilibrium. Now, this is our main air result. We are going to prove that that Pareto quasi-equilibrium, it is indeed a Pareto equilibrium. So what do we have here? For the case n, it is less or equal than 3, and we have a control V, then there exists a constant C that it depends on all these values and we have as constants, such that if mu it is large enough, then our functional, our convex combination, it is going to be indeed convex. Consequently, we have that if V hat, it is a Pareto quasi-equilibrium that we proved that exists because it was weakly lower semi-continuous, then we are going to have a Pareto equilibrium. Okay, so what are we going to do here? We are going to compute the second derivative, which is going to give us a function psi that it is going to be multiplied by the action W minus V, that it is the variation, where psi, it is the limit of the perturbation of the adjoint system with that epsilon, which is, and that psi, it is a solution of the following system. Again, this system, it also has a unique solution. It is well posed. Why? Because if we observe, it is the same as the adjoint. See, it is the same as the adjoint, has all the terms as the adjoint system, and the other terms are given and are bounded by the estimatives of the previous theorem. So it is the same, proving that this system is well posed and has a unique solution. Okay, it is just more terms that you have to do repetitively. So what do we need to prove? So we need to bound this term in order to prove that our function, it is convex. So what do we have here? Using the systems from 0, 7, 0, 8, and 0, 10, we have that this term, the first term of the second derivative, it is greater or equal than all these terms, okay? All these terms. And what we are going to do, we are going to apply the estimatives of theorem 3 and proposition 4. For what? We are going to apply those estimatives to bound these terms, and the bound, it is going to be a constant C multiplied with the term W minus V in the norm L2 omega S0T, all those terms. Similarly, we have these other bounds, and since n it is greater, it is less or equal than 3 by the Sobolev immersions theorem, and we have also the last term, it is also bounded by C, by a constant C multiplied by W minus V L2 squared. Okay, so Combining all of those estimates, and we have that this term, it is less or equal than that constant C multiplied by W minus V L2 in the norm L2 omega 0 T, where C, that constant C, it is a combination it is going to depend on all these terms, on all those terms that are known from our system. And therefore, we have the following estimates: that the second derivative evaluated in W minus V, it is going to be mu minus C by this constant W minus V. So if mu it is large enough than this constant C that it is given and fixed, then we have that J alpha it is convex, and therefore a Pareto quasi-equilibrium, it is going to be a Pareto equilibrium. That is the part for the non-bilinear system. Now, we have the case of the bilinear system. What says the case of the bilinear system? Here, the variation, it is that our control, it is acting in a multiplicative way with the state a variable. And here it is the catch for us. And we are also going to have the same hypothesis for the function A and the function F, the same hypothesis. And as again, but now, here it is the difference. The admissible control set, it is going to be L20T omega H01 omega. So we are taking the control set to be all those square integrable functions from 0t, such that the norm in the space a variable, it is bounded by H01 omega. Why are we using this? It is a technical requirement for making the energy estimates. If you have seen it before in the proof, we have assumed a regularity of order 2. That is, we have for our state a variable to be twice a differentiable in the space state. In this case, for that to be, for those energy estimates, we need the control to be in this space so that we can bound those integrals. This type of controls, it is not new. It has been used also in other works, but in other contexts. They also have those technical requirements, but they also have other technical requirements as implementation, but also as mathematical tools that are needed to make some bounds to work, okay? So under those a hypothesis for n equal 2, our system, it is going to accomplish the same energy estimates, and we are going to have that weak unique solution. So our functional, it is going to be modified. We are going to have JIV 1/2, the L2 distance of UT to UIT plus mu, and our regularization term, it is going to include what? It is going to include the gradient of B. That is, this is the H01 omega norm of V. So what do we have here? Again, if we are going to take also the convex combination, and when we compute the derivative, what do we have? We have the same thing as before. We have B mu, we have our derivative here, the part of the convex combination, plus the derivative of the norm in H01, where Z, it is the limit of the perturbed system of the derivative system, and U to the power U epsilon, it is the solution of the perturbed system by epsilon. So this is our derivative of the system, that it is also dependent on this W minus V, that it is the perturbation. And we also have the adjoint system, and the adjoint system, it is going to let us write our derivative in this form, okay? Minus U phi W minus V plus the term V multiplied W minus V with the sum of the product of the gradients, okay? And again, as before, assuming that the conditions on the functions a and f are satisfied as in the first case, with all those initial conditions and final ones, what do we have? And we have that the systems 019 and 020 are going to satisfy, again, the same energy estimates. And we are going to have what? That those energy estimates and we are going to have the weakly unique solutions and that are well posed. Okay, so those same energy estimates are going to help us bound the functional, the second derivative of the functional, so we can prove convexity. So again, and we have that if n equals 2 and mu it is greater than 0, for each alpha in 0, 1, there is going to be a control in this environment which minimizes the functional 0, 0, 18 with the gradient and norm, with this gradient norm, and hence we are going to have a Pareto quasi-equilibrium. The proof, it is the same one as we have presented before, using the energy estimates and those convergence criteria. Now, again, if for this second part, if n equals 2 and we have that constant mu greater than 0, we have that V, it is a Pareto quasi-equilibrium that corresponds to 0, 1. And we have our control that, and we have our W, our perturbation in L2 is S0T, then there is going to be a constant C that it is going to depend on all this, such that V, it is a Pareto equilibrium. And in this case, so if we have the Pareto quasi-equilibrium, and if we have that mu, it is large enough, which is going to prove convexity, then we are going to have a Pareto equilibrium. And again, we compute the second derivative of the system, which gives us another system that it is, again, well posed and has a unique solution, weak solution, and that is what we need. So with this system of the derivative of the adjoint, using systems 021 and 019, those systems of the derivative and the derivative of the adjoint, we have that the second derivative of, in the bilinear case, it is going to be greater or equal than all these expressions. So what do we have to do? We have to bound all these highlighted terms. If we bound those terms, we are going to be able to pick a mu such that it is going to be greater than the constant of the bound, and we are going to have convexity. Again, working on the terms on the right hand side of the above estimate 022, and using theorem T and proposition 11, what do we have? And we have that this theorem 3, it is the reference to the theorem of the well-posedness of the bilinear system, and the proposition 11, it is also the well-posedness of the derivative and the adjoint. We are going to have that these terms are going to be bounded again by a constant multiplied by W minus V and the norm L2 0T H01 omega. Okay, and we are going to have that norm. So therefore, proceeding as before, and we are going to have that our functional combining all our estimates with all our subvolute immersions and estimates, and we are going to have that if mu it is large enough than C, we are going to have that our functional it is convex, where C it is a constant that again it is going to depend from known parameters. Okay, so for mu large enough, and we are going to have that J sub alpha is convex, and hence the minimum.
Jose, you have 10 minutes. Okay,
and then V hat it is a unique, and therefore we have a Pareto equilibrium. For the case n equal 3, what do we have? And we have a control U. Okay, I am going to finish it. Okay, so and we have a control U. Our control set, it is all the V's such that V's are bounded almost everywhere. This control set, it is very used, it is very well, it is widely used in the literature because it is closed, weakly convergent, and convex. So it is a nice set to work. Again, for the case n equal 3, and we have using this set, and we have those energy estimates, and the system, it is well posed and performing again as before. It is very similar, but in this case, our functional does not have the regularization term with the norm in the Sobolev space. It is just in L2 because we have B bounded and performing the same computations, and we have our propositions, our well-posedness of the original system, and also of the derivative and the adjoint. And for n equal 3, and we have that, and we have our Pareto quasi-equilibrium and also our Pareto equilibrium. And the proof, it is similar for n equal 2. So that is the whole of the work. The rest, it is just part of the appendix, and that it is the proof of the well-posedness. And this last part I wanted to show to you, it is that why do we need, for example, in the case n equal 2, the control to be in the space H01, because here, this integral to bound it, we have the option of passing the Laplacian to a gradient, and again, we need this to be in H01, or we can use the Ledenskaya inequality, but again, with the Ledenskaya inequality, it is going to give us the derivative of the the gradient. That is the part why we use that control in H01. So that is the whole work, and it is just computations of the estimative of the well-posedness. And these are the references. Do you have any questions, any comments that you wish to make?
Thank
Hello?
you, Professor Jose Rodriguez, for your excellent talk. Now, your question, any question or commentaries, please? Any question or commentaries, please? For chat, for microphone.
Let me check the chat. I am not watching it.
No chat.
I'm
I have a question, Jose. In the case dimension n different 2 and 3, is possible application?
Could you repeat, please?
Dimension n 4, 5. Dimension rather or equal 4.
Well, I have not studied, but that may be an open question because those Sobolev immersion theorems depend on the dimension n and also on the regularity of the derivatives. So I will need to check these estimates, these energy estimates, to see how they work in dimension 4, and check the Sobolev immersions that are that lie within that context.
Yes, yes. Thank you, thank you. Other question? Other question? Good. If no more question, thank you very much, Professor Jose, again for your excellent talk, and see you.